So we've spent a good deal of time looking at equilibrium of a rigid body and then also putting that body into some different shapes, some frames and machines, presses. But now I want to look at, okay, what's going on inside of the body when forces are applied, right? So this is really important for us, especially as we go on to strength of materials, to know what forces are going on inside of the beam itself, inside of the body itself, because it's not always the same throughout the body, and it can vary at each different point. So today we're going to look at those different internal forces, what's going on inside of the body. And in 2D, we have 3 internal forces that we're going to see. So for our beam, imagine our beam here, and, we have our support reactions, and then some loading maybe. And we want to see what's going on inside the beam here. Call this point B. So here we would make a cut in our beam, see what's going on inside of the beam here. So here is my beam. And what I have going on in a 2D are 3 different internal forces. So I have my axial force. This is the one in the horizontal direction, the x direction. This is my axial force or normal force. We denote it with an N for normal. Axial force or normal force. And we also have a force in the y direction, so that's going to be our shear force. This is called shear force when it is through the middle of the beam. So shear force is denoted with a V. And interestingly enough, our positive convention for shear force is pointing downwards. So when you're looking at the beam on the left side, our shear force is going to be pointing downwards, and we consider that the positive direction of shear force. And then finally, we have a moment about that point. Moment. A bending moment about that point. So this feels kind of familiar to what we've seen before, right? Our 3 equilibrium equations where we were doing the sum of F, the sum of Y forces, and then the sum of our moments. Here our X force is the normal force, now called normal or axial force. Our Y force is the shear force, labeled with a capital V. And then our moment is our standard counterclockwise moment, labeled with M as we've seen it before. So these are the forces that a beam can be experiencing on its sides. We also have in 3D, can see some of these same forces, and they get a little bit different labels in 3D. So if we were to have this same beam, but now take it in a 3rd dimension, what we would have is a normal force along the axial. So along the length of the beam, we have the normal force. And now we have 2 directions for the shear force. So the Z direction and the X direction will both experience a shear force. Right, so these go along with the cross-section of the circle, whereas the normal force is perpendicular to that circular cross-section. And then finally we have our moments. Now, sometimes you'll also hear the moment about Y here. Moment about Y here, also called torsion, which is labeled with it looks like a capital T, but it's actually the capital Greek letter tau. Sometimes you'll hear it referred to as torsion, a twisting sensation of that bending moment that is around the normal force, that is around the axial force. We'll sometimes hear that called torsion. Another thing to note about these internal forces is that their forces are equal and opposite, right? These internal forces, if you split the beam at one location, say right here, when I have two halves of my beam, it works a lot like how we saw in frames and machines, where if our normal force is going positive in the x direction on the left-hand side of the beam, it is now going to be positive pointing to the left on the right side of the beam. Same with our shear force. Shear force is pointing down on our left side of our beam and points up on our right side of the beam. And this is what we consider to be the positive convention. So this is what we expect to see. If they turn out opposite of this, right, if you get a negative resultant from these assumptions, we'll just leave it as a negative. So this is what our beam would look like split into if we needed to solve for each side of the beam, for example. So these are going to work a lot like our frames and machines problems that we were doing, can be similar to our equilibrium of a rigid body, where we're going to go through this procedure of analysis. So our first step is going to be to draw the free body diagram for the full system. And solve for the support reaction. Our next step will be to draw a free body diagram where we want to know those internal forces. So splitting our original free body diagram and drawing a new free body diagram where we want to find the internal forces. And then finally, we'll apply our equilibrium equations. To solve for any unknowns. So our unknowns here, typically all three of our internal forces are our unknowns. So we are solving for that shear force, bending moment, and normal force. Typically what we're trying to find, we're finding our internal forces. So let's take a look at some examples. So in this example, it asked me to find the internal forces at point B and point C. So point B is just barely to the left of 6 kilonewton applied force. Point C is just barely to the right of the 6 kilonewton applied force. And really what this is going to do is show us that at different points, even though they're so close together, at different points, we're going to see different internal forces. So we have this beam, it's supported by a roller at A and a pin at D, and our very first step in this is finding our support reaction. Always going to be our first step, unless we can get away without it, but in this case, when we split up our beam, we're really going to need to know these support reactions. So if I draw my free body diagram first, that's always my first step, is I'll make a free body diagram over here. I have my support reaction at A. It's a roller, so it only has that y direction force. And then I have one at D, dy, and dx. And then, of course, those applied forces that were already there. So the moment of 9 kilonewton meters at D, and the applied force of 6 kilonewton. So now with this free body diagram, I can go ahead and set up and solve my equations for the reaction. So for this example, I'll take a moment at D so that I can find what AY is. I take a moment about D equals 0, set up that equilibrium equation. I will get my applied moment is included in this equation, so I'll get a positive 9 plus 6 kilonewtons times its distance away. It's 6 kilonewtons times 6 meters away, minus AY times its distance away from D, which is 9 meters. Punch that into my calculator, and I get that AY is 5 kilonewtons. And then of course I can set up my other two equilibrium equations. So my sum of forces in the y direction equals 0. Going to be my AY is 5 minus the applied 6 plus dy. So my dy reaction is going to be 1 kilonewton. And then of course by inspection I can just see that dx would be 0. Right? No other applied x forces, so dx is 0. So now that I have these reaction forces, I can go ahead and split my beam and draw a free body diagram. You can use either half that you want to. So you can use the segment from A to B or from B to D to solve for those forces at point B. Just note your sign convention, right? Note that whether you split it here or here, which way you're going to be drawing your forces for positive convention. Right, so your normal, and your moments. But it doesn't matter which side you choose, as long as you keep the sign convention straight. So I'm going to go ahead and do segment AB. Give myself some room here. So if I look at segment AB, here's my segment. I know AY we just found was 5 kilonewtons, sorry, 5 kilonewtons. And now I want to draw those internal forces at point B. And again, point B is just barely to the left of that 6 kilonewton applied force, so it's not going to show up on this free body diagram. Instead, it's only going to be that shear force, the normal force, and then the moment. So again, now with this free body diagram from segment, this is segment AB, I have my 3 unknowns and 3 equations, so I can go ahead and solve, right? Again, by inspection, if I do the sum of my x forces equals 0, I'm again going to get the normal force is 0. So normal force is 0, there's no axial force running through the beam. Next, I can do my sum of y forces equals 0, which will be my AY, so 5 kilonewtons, minus V. So V equals 5 kilonewtons, right? And the reason that it ended up positive is because we assumed our positive is down for the shear force, right? We assume that that's the correct direction. So it is the correct direction, so it ends up as a positive number. Now for my sum of y forces, I assumed that up was positive, which is AY, 5, positive value, but V was a minus V, because it's negative in the y direction. And finally, I take a moment. I'll take my moment about point B equals 0, and that will be the applied moment that I have at B minus 5 times its distance away, which is 3 meters. That gives me a moment of 15 kilonewton meters. And that may be slightly off by a decimal place because B isn't exactly at 3 meters, right? That 6 kilonewtons is at exactly 3 meters. It is very, very slightly to the left, but this is a close enough rounding to account for that very, very minuscule distance. So that's it. It's really the same process we've been using as the solving for support reactions, solving for trusses, solving for frames and machines. It's an application of these 3 equilibrium equations, just looking at the inside of the beam. So these were our ones for point B, but how would this differ at point C? Right, so I'm going to write these over here. My normal force was 0, my shear force was 5 kilonewtons, and my moment was 15 kilonewton meters. So let's take a look. If we were to draw this, instead of for segment AB, Now this is for segment AC, and we want to look at this force at point C. And notice the main difference is that point C is slightly to the right of that 6 kilonewton force, so it will be included on this free body diagram. Right, that 6 kilonewton force is going to be right here. So now when I go through and solve, of course my sum of x forces still 0. It had no impact on that, so the normal force is still 0. The sum of my y forces equals 0 is going to be 5 kilonewtons minus v, but also now minus that 6 kilonewtons, that applied 6 kilonewtons. So my shear force now is a negative 1 kilonewton. Right, so even though B and C were at very similar points, they're very close to each other, they have different shear forces at that point because of the applied force. And if I take a look at my moment, I'll take a moment about C now, equals 0. I'm going to say my 6 kilonewtons is a close enough applied force to being right on top of C that I'm not going to include it in this calculation. So I'll have M minus 5 times 3. So my moment will still be the same, 15 kilonewton meters. But the point is that they can change throughout the beam. Different applied forces, different applied moments, distributed loads. These can all change how the normal shear and moment internal forces can all change. Right? The loads and support reactions all change all of these internal forces. So let's take a look at another example. In this example, it again asks us to find the internal normal force, shear force, and bending moment at point C. But now we have a little bit different shaped of a beam. So at A, it's supported by a roller, at B by a pin, and then to the left of A is this overhang area. And so since we want to find the bending moment, internal forces, normal force, shear force at point C, what we have is a really interesting case where, depending on where we split it, we don't actually have to solve for the reaction force. So normally our first step is to draw a free body diagram and solve for those support reactions. But we'll notice if I go ahead and split my beam at point C and use the left side of it. I use the left side of my beam here. Here's my beam. I have that 4 kip force here, 4 kip applied force. I have the distributed load of 250 pounds per foot. And then I have those internal forces at C. But notice no reactions are actually captured in this half. This portion of the beam does not have any support reactions, so we don't actually need them to go ahead and solve for these internal forces. This free body diagram of the section from the left end to C is good enough. It's all we need to solve this problem. So I can just skip the first step of solving for all those support reactions and go straight to solving for the internal forces at C. So again, I'll apply my 3 equilibrium equations, my moment, my force in X, and force in Y. I'll go ahead and start with a moment. That's just my preferred. I like to start with the moment equation, and I'm going to take the moment about point C so that I don't have to include the shear force or the normal force. So about point C, which this is my point C right here. I'm going to have the internal moment. The internal moment is included, so moment. Then the simplified form of this distributed load. So this is 250 pounds per foot over this 4-foot distance here. 4-foot distance. 250 times 4 is 1,000. But if we'll notice, my other dimension is in kips. So 1,000 pounds equals 1 kip. So this is going to be 1 kip as the resultant force. 1,000 pounds, 1 kip. So here I have 1 kip, and times its distance away, going to be 2, since it's halfway between the 4. So that'll be a plus 1 kip times 2 feet, plus my 4 kips times 3 feet. This distance here is 3 feet. So that gives me a moment of negative 14 kip feet. So that tells me that my moment is actually going in the wrong direction, and that it's actually a clockwise moment internally on this left-hand side. So the moment, we'll leave it as negative, is a negative 14 kip feet. Solve for my y forces. Sum of forces in the y direction equals 0. I have a negative 1 kip minus my shear force. Those are the only two y directions. So my shear force must be negative 1 kip. Or negative 1,000 pounds. And finally, my x, sum of forces in the x direction, I'm going to have that applied force of 4 kips plus my normal force. Means that my normal force is negative 4 kips. Which tells me that my sign convention was flipped on all of these. So all of these are technically pointing in the opposite direction, but I'll just leave them in their negative forms, right? So normal axial force is negative 4 kips, shear force is negative 1 kip, and moment is negative 14 kip feet. Let's do one more example. In my last example here, again, I want to find those internal forces now at point D. But if we look at this beam that I'm given, I have a roller at A, a fixed connection at point C, right? So if I know immediately, if I were to draw my free body diagram for this, X, C, Y, a moment at C, my reactions for this beam, I have 4 reactions, right? But I have this internal pin at B. So at B, I have an internal pin, which means this works like our frame and machines problems, where I can go ahead and split it up at that internal pin at B, instead of having this 4-factor indeterminate form that I can't get anywhere with my only 3 equilibrium equations. So instead, I want to split the beam at B as we were doing with our frames and machines. I want to make a free body diagram at B to solve for those support reactions so that I can get somewhere to be around point D. So here, my free body diagram for segment AB is going to be my support reactions. I have a roller at A, so I have my Y reaction at A. I have a pin at B, an internal pin at B, so that gives me a BY and a BX. And then I also have this distributed load, this triangular distributed load, which I'm going to go ahead and simplify. So it acts 1/3 of the way in from the tallest side. So A to B is 12 feet, so 1/3 of 12 is 4. So it acts 4 feet in from the tallest side of the triangle in that area to find this magnitude. The resultant force is 1/2 times base, the length here, length of the bottom, 12 feet, times height, which is 1.5 kips per feet. So this gives me a resultant of 9 kips. 9 kips. So I can go ahead and apply my equilibrium equations to solve for the reaction.
And really I only need one side of this, right? Because my D point that I'm interested is here in the middle. I'm going, excuse me, I'm going to be doing another split again. So really I only need the A reactions or the B reactions. So in this case, if I take a moment about point B, I will get the 9 kips times its distance away is 4 minus AY times its distance away is 12, which tells me that my AY reaction is 3 kips. So now with that AY reaction, I can go ahead and make my split where I cut through the beam at point D and solve my equilibrium equations for shear, normal, and moment. Move this out of my way. I'll make a new free body diagram for this A to D segment. So we said AY was 3. I still have the distributed load, but my distributed load is different now. Notice that at point D, it's not the full 1.5 kips that it goes to up the top here. It only goes halfway through the triangle, so this high point on the triangle is 0.75 kips per foot. So when I simplify this distributed load, I have to remember that I'm breaking this up as well, and it's going to give me a new resultant force for this segment AD, and a new location for that. So here are my internal forces: shear, normal, moment, and then again, I want to write this resultant force in here, which is going to be 1/2 times base, and here the distance A to B, or A to D is 6 feet. 1/2 times 6 times height is now 0.75. So this gives me a new resultant force here of 2.25 kips, which acts 1/3 from the tallest side of the triangle, so 1/3 of 6, 2 feet. So that's my full and complete free body diagram, so now I can go ahead and solve for those internal forces. So I can take a moment about point D equals 0, and that will give me my 2.25 kips that we just found times it's 2 feet away from point D, minus AY is 3 times its distance away is 6. Plus, don't forget the applied moment here, right? The applied moments are always included in the moment equation. So solving, that gives me my moment is 13.5 kip feet. Just plugging that into the calculator. Now, of course, by inspection again, if I do the sum of my x forces equals 0, I'm going to have my normal force is 0. And then finally, the last of the 3 equilibrium equations, sum of forces in the y direction equals 0, is going to be that negative 2.25 kips plus AY is 3 minus the shear force. So that gives me my shear force is 0.75 kips. So again, all of these are very similar to things that we've been doing. It's just splitting your beam and knowing how the beam changes when you split. How do the distributed loads change, your resultant forces, which reactions do you actually need to know and use to solve for these internal forces, and then most importantly is probably your sign convention.
So knowing that shear points down, you're looking at the left side of the beam, points up when you're looking at the right side of the beam, keeping in mind these sign conventions to solve for these internal normal force, shear force, and bending moment within the beam itself.